Question 6 from the 2025 Higher Physics Question Paper 2. The following statement represents a nuclear decay in which an alpha particle is emitted. And they are given the reaction there. 241 AM95, and that breaks in to give you 237 NP93 plus the helium particle 42He. And for 1 mark, we're asked to explain why energy is released in this decay. Well, it comes from the fact that if we take the masses on both sides of that nuclear reaction, if we take the mass on the left hand side and compare it with the total masses on the right hand side, we get something like this. We can see that there's going to be less mass on the right hand side of this equation. So where is that mass gone to? It's a missing mass. There's a defect in our calculation. In fact, that's why we call it the mass defect. So why is energy released in this decay? Well, it's quite simply that the total mass on the right hand side is less than the total mass on the left hand side of the reaction, and this means there's a mass defect and mass is missing, and this mass has been converted into energy. And of course it's been converted into energy, as we'll use in the next calculation, by the fact of the conversion rate. Energy equals mc squared, Einstein's famous mass energy equation. So for 1 mark, it seems a lot, but for 1 mark, all we need to say is that mass is missing on the right hand side of the nuclear reaction. It is missing because it's been changed into energy according to E equals mc squared. And in the second part of this question, we'll probably be asked to find that energy. And here we go in this case then. What we have is we have a table and it says the mass of the particles involved in this decay are shown in the table below. And the masses are very, very accurate in this case then. So we've got the americium on one side and the products on the other side. A wee quick recap of the nuclear reaction. That's it there. And we're given it masses. All we have to do is work out the masses on both sides of that equation. And we can use a calculator, be very careful, and we find out the total mass we're given on this side of the equation is 4.0028 times 10 to the minus 25 kilograms. And if we take the individual masses from the table on the right hand side and add them up, we get 4.002747 times 10 to minus 25 kilograms. Just be very careful of that minus 27 there when you're putting it into your calculator. So you can see from the two figures there that we definitely have a mass defect. The masses added up on this side are definitely less than the mass on this side. So to find the mass defect, we just simply subtract as follows. So we can just do the following to subtract. We can say that the masses on the right hand side is 4.0028 times 10 to the minus 25, and subtract this figure here, and we end up with that value there, which is going to give us a mass defect of 5.3 times 10 to the minus 30 kilograms. Just taking that mass and take this mass from it, and we get our mass defect. And as we said before, we're now required to use Einstein's energy equivalence equation. Energy is going to equal to mc squared. So we know the mass, the missing mass, it has to be converted into energy. So the mass we know is 5.3 from our calculation, times 10 to the minus 30 kilograms, and we have to multiply that by 3 times 10 to the power 8, the speed of light all squared. And if we do that in a calculator, we end up with a value of 4.77 times 10 to the minus 13 joules. Remember, energy is measured in joules. So the mass which has gone missing in that reaction has been converted into 4.77 times 10 to the minus 13 joules. Question 6 continued, part B. Carbon-14 undergoes nuclear decay by releasing a beta particle, E and minus 1, 0. The following statement represents this decay, and you have the statement there, and for 1 mark we're asked to identify the element represented by X. Well, first of all, we've got to compare the mass numbers. So we go to our equation and we compare the mass numbers. So we have the mass numbers here. Remember, the mass numbers are the ones which are at the top. That's these ones here. And we can say we have got, on the left hand side, we have got the following. We have got 14. And that should be going to give you an unknown mass number, which we'll call M, and it's going to be plus the 0. So therefore that implies that the missing mass number has got to be equal to 14. Let's look at the atomic number, that's the bottom ones. And we have 6 on the left hand side, and on the right hand side we have our missing atomic number, which we'll call n, and we have a -1 here. So that implies that n must be equal to 7. So our missing elements should have the following form. It should have a mass number of 14, it should have a atomic number of 7, and if we look that up in our data sheet, especially our periodic table, the mass number, the atomic number 7 is going to give you the elements code, and it's going to be, in this case, it's going to be nitrogen. So it's going to be N for nitrogen. So our missing element is nitrogen. Missing element will be nitrogen. Atomic number 7 and the mass number 14. Question 6, part B, part 2. An explanation for beta decay is that a neutron decays into a proton and an electron. The electron is emitted as a beta particle. However, studies of beta decay show that the mass energy equivalence of carbon-14 is greater than the total mass energy equivalence of element X and the beta particle. And for 1 mark, we asked to state the conclusion that particle physicists have drawn from this evidence about what happens during beta decay. Well, there's our example up there. We can see we're going to have 14, carbon-14, 6, and it's going to decay into the nitrogen, as we worked out there, nitrogen 14,7, and it's going to release a beta particle, which is really fast moving an electron. And as we're told in the question here, the fast moving electron really comes from the result of a neutron decay. Now, it's this phrase here, the total mass energy equivalence, and that means the mass and the energy. But remember, mass and energy are interchangeable when we come to talk about atomic nuclear physics. Mass and energy are the same thing. Mass, energy. The equivalence factor is that the energy is equal to mc squared. So if we've got some mass, we know how we can change it into energy by multiplying by c squared. But when we look at this reaction, we find out the total mass energy of this side and add up the total mass energy of each of these, we find out that there's something missing. That is bigger than this here. So in order to balance out the total mass energy equivalence, we have to have another particle here. And we'll call that particle the neutrino, because then we have the mass energy, total mass energy of this particle here, this nucleus here, and then we have the total mass energy of the nitrogen one, total mass energy of the beta particle, and we find out we have to include the neutrino, a missing particle here, to make sure that on both sides the total mass energy is balanced. And that was proposed that there should be this neutrino particle. Neutrino means little one, and lo and behold, they did discover the neutrino. Very hard to discover, but that's why we need to have a neutrino in here in order to balance up the total mass energy from both sides. That energy should equal to that energy, mass energy, plus that mass energy, plus that mass energy. So we need to have a neutrino to explain the beta decay. Question 6 continued, part C. Quarks are fundamental particles that do not exist by themselves, but make up other particles called hadrons. There are 6 types of quark. They are the up, down, charm and strange, and top and bottom. And for 1 mark, we asked to explain what is meant by the term fundamental particle. Well, a fundamental particle is one which cannot be broken down any further into any further particles. That's the key for that. A fundamental particle is one that can't be broken down into any more constituent parts. That's what it means by fundamental. Part 2. Hadrons can be further classified according to the number of quarks they contain. State the name of the particles that contain 3 quarks. Well, if we've got 3 quarks, then what we have is a baryon. So the answer to that is a baryon. Of course, the other one would be the meson, and of course the meson would have a quark and an antiquark. So the answer to question 6C2 is that it's got to be a baryon, A baryon is a particle which contains 3 quarks. Question 6c, continued part 3. Scientists have discovered a type of particle called a pentaquark. Pentaquarks contain 4 quarks and an antiquark. Penta means there must be 5 of them there. Now, recently scientists at CERN, the Centre for the Nuclear Research for Europe, reported that the discovery of a pentaquark contained 1 up, 1 down, 1 strange, 1 charm and 1 anti-charm quark. And the table contains information about the charge of some of the quarks that make up the pentaquark. The overall charge of the pentaquark is 0. And for 2 marks we're asked to determine the charge on the strange quark. Okay, let's line up all the quarks like that, and let's put down their charges below it. So the up quark has got a charge of plus 2/3 of an electron, so 2/3 of an electron there. The down quark has got minus 1/3 of an electron. The strange quarks we don't know, so we'll call that X. Don't know what that is. And we do know that the charm has got plus 2/3 of an electron for its charge, and the antiquark will have a charge opposite of that. It will have a charge of minus 2/3 of an electron. So if we add this all up, we have 2/3, take away 1/3 is going to leave you with 1/3. So we only have plus 1/3 of an electron here, plus the X, plus on this side here 2/3 of an electron. Take away 2/3 of the electron leaves you with 0. And we'll get that equal to 0. And that all added up must be equal to 0 itself, because remember the charge on the pentaquark is 0. So we've got a simple equation we can rearrange. We can say that plus 1/3 of an electron is plus the X, the charge on the strange quark, must be equal to 0. And therefore that implies that the charge on the strange quark must be equal to minus 1/3 of an electron.